this video we will talk about the idea of inverse filtering. The topic is inverse filtering. In the previous lecture we have seen that suppose that we have an image f of xy, and if I convolve it with a degradation function h of xy, and if I add an additive noise eta of xy to this one, then I will get a resulting image. We will call it as the degraded image, or we will represent it as g of xy. Now suppose that if you take the Fourier transform of this particular equation, so in the frequency domain we can write the same process as g of uv equal to f of uv into h of uv plus n of uv, where each term in this equation represents the Fourier transform of the terms in the first equation. Now when we talk about inverse filtering is actually used for image restoration. So the image restoration is the process of estimating an image from the degraded image. So we have the equation of g of xy, or we have the degraded image g of xy and its Fourier transform g of uv, and according to inverse filtering, we can find the degraded image or its Fourier transform f hat of uv just by taking the degraded image and dividing it by the degradation function. If we can get an idea about the degradation function h of uv just by simply dividing the degraded image with the degradation function, will give you the estimated image or its Fourier transform. And if you substitute this equation, that is g of uv equal to f of uv into h of uv plus n of uv into this one, that is, so substituting this value over here, then I can write f hat of uv equal to f of uv into h of uv plus n of uv all divided by h of uv. Now if I take the same equation for further simplification, I'm making a copy of it, then I'm putting it over here. Okay, so this is equal to the same equation. Now if I split this h of uv to the numerator and denominator separately, then I can write it as, I'm taking a copy of this one and I'm giving a copy to this part, and I am giving a copy to the first part. Then if I split the ratio among numerator and denominator separately, then this is the term that I can write. Now if you look at the first term says that we are multiplying with h of uv and we are dividing it with h of uv, so there is no final effect for that operations, so I can just write it as f of uv, and I cannot do anything with the other term because we have n of uv and h of uv in the denominator. So this is the estimated image Fourier transform, that is f hat of uv. Now if you look at this equation, there are two problems. The first one was, if you do not have this term, then we will get the exact restored image, or we will get the original image back. And on other hand, if you have this part existing, then there are two problems. The first one is we cannot estimate the values of n of uv, that is n of uv is unknown. Okay, and the second problem is, imagine that if this h of uv is getting a very smaller value. Okay, so that is if h of uv is very very small, then n of uv divided by h of uv will dominate over f of uv. That means this term, if h of uv at some point is very small, then n of uv divided by h of uv will be very large, then that will be much greater than f of uv. So that will be further distorting my image. So these are the main problems of inverse filtering, that is n of uv is completely unknown. We can estimate the probability distribution function of n of uv or n of et of xy, but we do not know the exact values of n of uv. If we have known the values of n of uv, we just need to subtract n of uv divided by h of uv from this entire equation, then you will get the exact values of f of uv. But these values are not to be able to be identified or estimated, so the value of n of uv is completely unknown. The second case is, at some point this h of uv will be can be very small, so in that case this term will be much larger than the first term, which means that the error is contributing more than the original image. Now we have to look at how we can mitigate this problem of uh, domination, the dominant part of n of uv divided by h of uv. For that, most of the time, or in certain examples, our h of u will be having a shape of this kind. So when you look at this diagram, you can see that there are certain values which are larger values in the middle of the filter h of uv, and if you move away from the circular part, or if you move away from the values which are distant from the center, then the values are becoming zero. So you can also see from the radial cross section of the filter, that is h of uv has a higher value in the center, and you move as you move away from the center, the values are becoming very large. So the large values of u and v, or the large value of u and v, we will have the values of h of uv very small in certain cases. So what you will do is, you will find the value of, you will take the Fourier transform of the degraded image, that is g of uv, then you divide it by the degradation function that you got by some method. Then you will not take the complete value of this ratio, you will confine the value to the values to a smaller circle, and you just neglect all the values outside this circle. So in that case, you can actually remove the higher values that is happening in the ratio g of uv divided by h of uv. So when you get the values of n of uv divided by h of uv very small, we neglect, usually what we will do is, we will fix a circle of certain radius, and then you just omit the values outside the circle, then you take the values inside the circle for your calculation and assigning all other values to 0. So in that, by doing that, you can actually omit the value which are very larger in the ratio g of uv to h of uv. So here we have given an example. So this is my degraded image, and these are the four outputs after the restoration process. The first one is the direct inverse filtering. Direct inverse filtering means you are just dividing the degraded image by h of uv. So we'll have f of uv and certain values of the values of n of uv divided by h of uv. And if the values of h of uv is very small, then obviously this value will be very large. And in the first example, we didn't neglect those values, we take that into consideration. So you can see that this is completely blurred image, we cannot identify what the object is. And the second one is you are actually neglecting the values of g of uv divided by h of uv beyond the radius 40. And in this case we are neglecting the values beyond the radius a 70, and in this case we are neglecting the values beyond the value of radius equal to 85. So these are three cases which are much better than the direct inverse filtering. So here when you see that if you are reducing the neglecting values beyond 40, you are actually missing certain frequencies. And here you can see that 70 is a good value of the radius, because you can see the original image in this particular value or in this particular image. And if you go beyond the value 70, suppose that you are fixing the value of the radius equal to uh, 85, then you are actually getting some noises, or the noise part is dominating over the image part. Okay, so this is the idea of inverse filtering. We can use it with the fact that there can be some distortions by the dominant contribution from the noise, but if you can mitigate that by restricting the radius of the ratio of g of uv to h of uv, then you will get satisfactory output. I hope it is clear. Thank you very much.